December 27, 2024. NASA's Juno spacecraft swings past a small moon in Jupiter's system. Not a close flyby this time. The spacecraft is 74,000 kilometers away. Far enough that scientists weren't expecting much. What happened next made the mission's principal investigator say, "On the record, the data from this flyby really blew our minds." The infrared detector on board, an instrument designed to measure heat, completely saturated. It maxed out. It hit its physical limit, because what Juno had just witnessed was the most powerful volcanic eruption ever recorded anywhere in the solar system. Not just on this moon, in the entire solar system. In the history of space exploration. And the eruption was still going. Weeks later, months later, scientists believe it's still active right now. This is Io, Jupiter's innermost large moon. And what NASA has found there in the last 18 months has rewritten almost everything we thought we knew about how volcanoes and planets actually work. To understand what makes Io extraordinary, you need to understand what it sits next to. Jupiter is the largest planet in our solar system. It's so massive that 1,300 Earths could fit inside it. Its gravitational pull is so powerful that it doesn't just affect objects in orbit around it. It physically deforms them, stretches them, squeezes them, changes their shape. Io sits 350,000 kilometers from Jupiter, roughly the same distance as Earth from our moon. At that distance, Jupiter's gravity is relentless. But Io doesn't orbit in a perfect circle. Its path is elliptical and oval. So sometimes it's closer to Jupiter, sometimes further. The gravitational pull varies constantly, and with it, the amount of squeezing. On Earth, the moon's gravity pulls up our oceans by about half a meter during high tide. That's water, fluid. It responds easily. Jupiter pulls up Io's surface, solid rock, by as much as 100 meters. 100 meters of solid rock, stretching and compressing every 42.5 hours as Io completes each orbit. And generated by that constant deformation is extraordinary. It generates heat, not just on the surface, but deep inside the moon's interior. And that heat has to go somewhere. It goes up, through 400 volcanoes. Io is the most volcanically active body in the solar system, by a significant margin. Not slightly more active than the runner-up, incomparably more active. A world in a permanent state of geological fury, reshaping its own surface continuously, driven by a gravitational engine it has no control over. Now let's talk about what Juno found on December 27, 2024. Because this is where the story goes somewhere nobody expected. Juno's Jovian Infrared Auroral Mapper, JIRAM, detected an event of extreme infrared radiance in Io's southern hemisphere so strong that it saturated the detector. Alessandro Mira, a Juno co-investigator from the National Institute for Astrophysics in Rome, described what they were seeing. Not one volcanic hotspot, but what appeared to be several closely spaced hotspots firing simultaneously, suggesting a subsurface magma chamber system of enormous scale. The hotspot is not only larger than Earth's Lake Superior, but it also belches out eruptions 6 times the total energy of all the world's power plants. 6 times. The total energy output of every power plant on Earth, combined, from a single volcanic feature on a moon slightly smaller than ours. And it didn't stop. Looking at JIRAM data alone, the team determined that the most energetic eruption in Io's history was still spewing lava and ash as recently as March 2, 2025. Scientists believe it remains active today. Not dying down, not cooling off, still going. Months after it was first detected, Scott Bolton, Juno's principal investigator at the Southwest Research Institute, said it plainly, "This is the most powerful volcanic event ever recorded on the most volcanic world in our solar system." Here is the question that had been sitting unanswered since Voyager 1 first spotted Io's eruptions in 1979. Where exactly does the heat come from? The obvious answer, tidal heating from Jupiter, was always known. But the how was the mystery. Specifically, does Io have a global magma ocean beneath its surface, like a planet-wide layer of molten rock churning underneath the crust? Or something different? For 44 years, nobody could answer that. In December 2024, a paper published in the journal Nature answered it. Juno's two close flybys in December 2023 and February 2024, getting within 1,500 kilometers of the surface, allowed the team to measure Io's gravity with extraordinary precision. By tracking exactly how Io's gravity tugged on Juno's trajectory during those flybys, scientists could infer what's happening inside the moon. The findings revealed tidal deformation consistent with Io not having a shallow global magma ocean. Instead, the volcanoes on Io are each likely powered by their own individual chamber of roiling hot magma. Not one interconnected ocean. Hundreds of separate, independent magma chambers. Each volcano its own engine. Each one behaving differently, governed by local conditions rather than a single planetary scale system. Lead author Ryan Park from JPL said, Juno's discovery that tidal forces do not always create global magma oceans does more than prompt us to rethink what we know about Io's interior. It has implications for our understanding of other moons, such as Enceladus and Europa, and even exoplanets and super-Earths. Think about that. A discovery about a volcanic moon of Jupiter is changing how scientists think about the potential for life in Europa's ocean, and about planetary formation across the galaxy. The April 2025 data from Juno added something else. Something that changed how we understand the entire thermal system of Io. By combining two of Juno's instruments, the JIRAM infrared mapper and the microwave radiometer originally designed to peer beneath Jupiter's clouds, scientists mapped, for the first time ever, the subsurface temperature profile of Io, not the surface, underneath it. Around 10% of Io's surface has remnants of slowly cooling lava just beneath the surface. A tenth of an entire moon, quietly glowing, not erupting, not dramatic, just cooling. A massive underground thermal blanket covering an area equivalent to the entire continent of Asia. Juno co-investigator Shannon Brown described the system with an analogy that I think is perfect. Io's volcanoes, lava fields, and subterranean lava flows act like a car radiator, efficiently moving heat from the interior to the surface, cooling itself down in the vacuum of space. A car radiator, a moon the size of ours, acting as a cooling system for the gravitational energy Jupiter constantly pumps into it. The volcanoes aren't just eruptions, they're exhaust vents. The lava lakes aren't just impressive, they're heat exchangers. The whole moon is a machine. And we're only now understanding how it works. Let's talk about what Io actually looks like. Because the images Juno returned are unlike anything in the solar system. The surface is dominated by color, not the gray and brown palette of most rocky bodies. Io is yellow, white, orange, red, and occasionally green, each color telling you something about what's happening beneath it. The yellow regions are crystallized sulfur, essentially sulfur snow, flash frozen by the extreme temperatures outside the volcanic zones, where the surface drops to -130 degrees Celsius. The white and blue patches are frozen sulfur dioxide settling in the coldest shadow regions. The red areas mark active heat, recent eruptions, still warm. And then there are the mountains. Not the shield volcanoes you'd expect, not mountain ranges built by tectonic collision. Just lone, jagged peaks stabbing upward from the surface. The tallest rises 18 kilometers, twice the height of Everest, standing completely alone with no nearby formations to explain it. The leading theory is that these mountains don't grow slowly, they burst upward. When the constant lava overflow causes the surface to collapse downward in one area, the pressure has to go somewhere. It pushes up, a new mountain appears, suddenly, with no warning and no geological narrative connecting it to anything around it. The most famous of these is Steeple Mountain, named because its profile looks almost exactly like a church spire. Juno is running low on fuel. It will not be orbiting Jupiter forever. And right now, there is no dedicated Io mission in active development. The upcoming missions, ESA's JUICE, arriving at Jupiter in 2031, and NASA's Europa Clipper, arriving in 2030, will both focus on the icy moons. Europa for the ocean beneath the ice, Ganymede for its magnetic field, Callisto for its ancient cratered history. Io gets the spotlight when a passing spacecraft happens to be in the right place. Which means most of what we know about Io came from flybys that weren't primarily about Io at all. Voyager didn't go there for the volcanoes. Juno originally went to study Jupiter's atmosphere. The most scientifically productive moon in the outer solar system has never once been the primary destination of a spacecraft. And yet, the December 2024 Nature paper, the most powerful eruption ever recorded, the subsurface temperature mapping, the resolution of a 44-year mystery, all of it came from a spacecraft originally designed to do something else. What would a dedicated Io mission find? Here's what stays with me about Io. It's a moon that should be frozen. It sits more than 600 million kilometers from the sun. Out there, everything should be cold, dead, and still. Instead, it's the most volcanically active body in the solar system, driven not by sunlight, not by radioactive decay, but by gravity, by the invisible, relentless grip of a planet that is incomprehensibly larger than it. Jupiter doesn't know what it's doing to Io. It doesn't care. It just pulls. And Io, caught between that pull and the competing forces of 3 other large moons, has no choice but to burn. The December 2024 eruption, the most powerful ever recorded, is almost certainly still going as you watch this. Lava is still flowing. Ash is still rising. The surface of Io is being remade, again, in an event that has no precedent in our entire history of space exploration. We found all of this with a spacecraft that came to study something else. Imagine what we'd find if we actually went there for Io.